And this is the plan for the presentation. We'll have a little bit of motivation for doing things with rational numbers. And so the rational arithmetic facility will consist of design for the representation, function for entering rational numbers conveniently, an operator capital Q for working with rational numbers, and then some examples of working with rational numbers. This is one of the motivating examples of for working with rational numbers. So in Dyalog' APL, or in any other APL actually, if you enter this expression, 7 minus 100 times 0.07, instead of getting a 0, you get this number, non-zero number. Even though I'm not a mathematician, this offends my mathematical sensitivities. So one of the ways to get around this is to work with rational numbers. So first we need a design for the representation of rational numbers. So the design that I'm using here in this facility is to represent rational numbers as a scalar with 3 parts, each of which is enclosed. So you would enclose the decimal digits of the numerator, and then the decimal digits of the denominator, and then the sign. And the numerator and denominator are relatively prime. With this representation, 2 rational numbers are equal or matching if and only if their representations match. So some examples. 0.8 would be represented as 4/5, and the sign is 1 because it's positive. And negative 3.14159 would be represented as the decimal digits of the numerator, 314,159, and then the numerator is 1,000,000, and the sign of the entire number is -1. And because each rational number is represented as a scalar, you can just concatenate them together. So to represent the vector 0, -0.5 is just like this. The representation of 0 concatenated with the representation of -0.5. Of course, it's kind of onerous if you have to enter rational numbers this way with all the enclosures and concatenations and so forth. So part of the irrational arithmetic facility is a function qi, which converts an ordinary array of numbers into a rational array. So qi is 3.5 is the number 7/2, and qi of 3.5 -6 7.89 would be this 3-element vector, of rational numbers. And as well, it applies to enclosed arrays. And so if you have a rational numbers with extended position, you can just enclose the digits of the number that you want to represent, and qi would convert it into a rational number. So, and the denominator is assumed to be 1. And as well, you can give qi an enclosed character string. using the same exponential notation permitted for ordinary numbers, except the range is unlimited. So this is a number that you can't work with in ordinary APL, but with this rational arithmetic facility, you can work with them by first giving it to QI. So here we have a number with an extremely large magnitude, and the second one with a rational number with an extremely small magnitude. Okay, so now having these rational numbers, it's how do you work with them? Well, there's an operator Q. Oh, by the way, the code is available as a workspace that you can download from the Dyalog'20 conference web page. It's available for download now and also after the conference. And also the presentation, the slides of this presentation is also available from the conference web page after the conference. So the operator Q, capital Q, accepts a function argument, of course. And for scalar functions, instead of saying, for example, plus, you just say plus Q. And it requires the arguments to be rational, so you have to apply QI to the arguments. And it does it and returns a rational number result, usually. And so if you have an operator expression involving scalar functions, you just apply Q to the scalar function argument, and it would do it. So this is plus slash on 3, 4, 5, 5, 6 as rational numbers, you get 27/2 or 13.5. And if the operating function to Q is a structural or selection function, not to Q. If the function you want to apply is a structural or selection function, you don't need to do anything. It just works because the representation is that each rational number is a scalar, so you don't want to reshape an array of rational numbers. You just say reshape. And likewise for selection functions like indexing. So A, for example, A here is a 2×3 array of rational numbers. In A, row 1, column 0, 2, row 1, column 0, row 2 would be, here's a 2 and this 0, I'm sorry, 0. And for other functions, you do have to apply Q to the function operator to get it to work on rational numbers. And a little bit surprisingly, the most important of these other functions is the format function, the thorn. So this rational matrix A that we have here is kind of wonky to look at, but if you apply thorn Q to it, you get something that's more compact and maybe more easily understandable. And the output notation is that the numerator and the denominator are separated by the letter R. So, and on the right here, we have dyadic use of the format primitive, thorn Q. So here we have 2 to the power 5, 6, 7, 8, 9 displayed in exponential notation, which is what the negative left argument to Thorn gives you with 20 significant digits. So here we have 2 to the power 5, 6, 7, 8, 9. With only the first 20 digits displayed. I mean, it's a lot of digits if I display the whole thing. So, some examples of using rational arithmetic. First one are continued fractions. So, to work with continued fractions, this is a plus composed with reciprocal is a essential function. So if we work with ordinary numbers, you get something that looks like you'll approach the golden ratio, the 1.6178, so forth. Actually, yeah, okay. But if you work with rational numbers, both the rational calculation and the rational calculation, so instead of 11 row 1, I have 11 row or reshape of the rational number 1, and I do plus reciprocal scan of it. I get this rational number result, and lo and behold, we see our friends, the Fibonacci numbers. And I went to the online encyclopedia of integer sequences, sequence 1203, getting this vector, and I apply the continued fraction calculation on that as a rational vector. And then I display, make it a one-column matrix. That's what the comma bar does. And then format it using 30 decimal places. And I get pi. Isn't that delicious? There's a pun there. I hope you all are laughing, or at least smiling. Okay, next example is square root using Newton's method. As you know, square root is not a rational function, but we can get rational approximations to function square root values. So here is square root 0, working on ordinary numbers. So I apply Newton's method 8 times to find to find approximations to the square root of 2. And if also on ordinary numbers, I get this. So as you can see, it's approaching the square root of 2. So display, so and T is the 8 approximations. So this is a display using 15 decimal places of the approximations themselves and the error in their approximation. Okay, so this is for ordinary numbers. So what happens with rational numbers? So I convert the function from working with ordinary numbers to rational numbers, and so represent the numbers, or convert the numbers into rational numbers, and then using rational calculations, plus q and divide q plus q and divide q, and then and here we go. And by the way, this expression can be equivalent to f to the power iota alpha qf1. So if I had to extend some primitive, the first thing I would propose is to extend the power operator to work on array right operands. Anyway, calculating the applying the function to rational arguments using rational computations, I get pretty soon I get numbers with huge number of digits. And this is the equivalent display to the previous slide. The approximations themselves using 40 decimal places. So this really illustrates that Thorne Q is a very useful computation indeed. And then the errors in the representation. So this illustrates the right hand column in this display illustrates the fact that Newton iteration gets you double the number of correct digits from iteration to iteration. Okay, next, matrix inverse. This is a particularly annoying thing with working with floating point numbers is a matrix inverse or matrix divide. That you go through all sorts of contortions, and in your algorithm, when you get, when you get a zero, you have always, or a very small number, you have to wonder, is this truly a zero or is that just a small number? So to illustrate that, I'm going to use the Hilbert matrix. So even in the display, in the display of it and the representation of the Hilbert matrix, you can see that it's already better than floating point numbers. You can see the structure much better. Now the Hilbert matrix is proven to be invertible, but it's also proven to be extremely close to being singular, being very close to being non-invertible. So I've converted it to rational numbers. So A is a rational matrix, and apply matrix inverse to it. And when I do A times the matrix inverse of A, using plus dot times, but working with rational numbers, I get the identity matrix. No ifs and buts or whatever. That is identity matrix. In contrast, if you work with rational number, ordinary numbers, ordinary floating point numbers, this is what you get. And this is supposedly identity matrix. But you get all this other crap, which is close to zero, but are they really zero? I guess they really should be zero. Okay. What about for other matrices? So I'm just going to work with a random matrix, 6 by 6 matrix, and then multiplying the matrix by its inverse. And then the rational version. First, convert the argument, convert the matrix into rational numbers, invert it by using domino Q, and then doing the matrix product using rational arithmetic, and get the identity matrix. So going back to the original example, which is one of the examples which motivated working with rational numbers. So if you work with rational numbers, 7 minus 100 times 0.07, you do get 0. Oh, good. I see I still have a little bit of time, so I will give you a glimpse of what's can be coming next. Now, there are non-rational numbers, non-rational functions such as the exponential functions. So what I was working on before the QA and the code coverage thing intruded, which is rightfully has much higher priority. So anyway, before that, I was working on something which I call big floats, namely floating point numbers with as many digits as you like. So here I specify that I want floating point numbers of 80 significant figures. And then like the rational numbers, away from share application. What is that? No. I hope that's better. So as to repeat, I specify 80 significant digits in the
Roger, what it is you're showing we can't see. It's just a black box.
Oh, can you see it now?
No, it looks like you might be trying to share Zoom. It's blanked itself.
Oh, dear. Let me see.
If you are trying to share Zoom, you can't do that. Zoom won't let you share Zoom.
I'm not trying to share Zoom. I'm trying to share my dialogue session. Well, anyway, never mind. I'll just speak through it. The thing that I'm working on is called big floats, where you can specify the number of digits in your floating point numbers. And the example I was hoping to show is the calculation of e to the 1, the Euler's number. Okay, that's too bad that I can't share that. Yeah. Okay, that's the end of what I have to say. Any questions?
There are some questions. I don't know if you can, well, not yet. I'll read them out to you. Let's see.
Yeah.
There is a question about how to decompose an Egyptian fraction by 1 over n.
It's been a while since I looked at Egyptian fractions, so I don't have an answer immediately.
Okay.
So the next one is from Rodrigo.
Yes, you can see them.
Yes, what happens if we use QI on irrational numbers? No problem, because you cannot enter irrational numbers in Dyalog' API anyway. You have to represent it as floating point numbers, and QI works on floating point numbers, no problem. Any numeric array other than complex numbers that you can enter in, that you can have in Dyalog' API, QI will work on it. What will show when you give in the irrational numbers to QI? Okay, no, it'll give the best. So Shu Hao has a question. What will show when you apply QI to an irrational number? I think I've already answered that, but let's say you apply QI to 2 star 0.5, where 2 star 0.5 is supposedly an irrational number, but it's a floating point number. So you'll give the best rational number representation that it can to it. And and the QI has in the slide, in the text of the paper for this presentation, it will tell you that QI has a left argument, which is the tolerance you want to use to compute a rational representation. So QI on a number will use the quad CT that's in the workspace. But if you want to be as exact as possible, you give a left argument of 0. It'll give closer approximation to the number using quad CT of 0. Another question from Darwin Church is, where can we download QI? It's available for download in the conference page right now from the Dyalog' website, the Dyalog' conference webpage. Aaron has the question, have you thought much about the performance of these operations at large sizes with many values? I have thought about it. I believe that the performance will be improved if only we have a better multiplication algorithm for extended position numbers. So things such as a GMP will help. But otherwise, I think it's okay. The performance is okay. Okay, Dieter has a question that my representation is not numerators and denominators positive. And he has a model allowing the numerator all integers so that I need no sign. Why did you choose a model with a sign instead? I'm not sure that. Okay, in this representation, I can work with positive and negative numbers without extra thing. I'm not sure that answers your question. Because if your model has numerators and denominators both positive, I'm not sure how you get negative numbers. That looks like that's any other questions? Okay. Dieter says that the numerator may be negative in your model. That's fine. Yeah, it's okay. I just find having a separate sign easier to work with. That's all.
Okay, that looks like the end. Complex numbers, there's a question.
No, it doesn't.
Quick answer.
But you can write an application on top of that using pairs of rational numbers, and then you get rational complex numbers. Okay.
And maybe we'll take one more question. Marco asks about normalization. Prime numbers.
Normalization. Is that one question or two questions?
I guess he's talking about reducing the fractions.
Okay.
Would be my guess.
Well, you just find the GCD of the numerator and denominator, and then you divide both by that GCD, and then it's in lowest terms. Okay.
Okay. Right. Well, bang on time. Thank you very much.